Okay, so one of the things that got lost in all the NVIDIA announcements last week was that they also released a new ASR, or rather a streaming ASR model. So this is the Nemotron 3.5 ASR model. And this is basically a 600 million checkpoint that can probably replace your whole speech to text stack in here. You can basically self-host it. You can get it to do a whole bunch of the features like streaming audio and stuff like that. In this video, I'm going to talk about the model. I'm going to talk about some of the things around it, and I'm going to go through some demos of actually how well it does for streaming audio, how you can use it to do things like word boosting to make it more accurate for your particular use case, and also how you can use it in a diarization system to be able to get speaker level attribution, etc. So up until recently, most of the streaming ASR models that you could actually self-host, things like Whisper, etc., were great for sort of offline or batch prediction, but they weren't really any good for streaming use cases. So what NVIDIA has released here is a 600 million parameter streaming model that can transcribe 40 languages from a single checkpoint. And this is coming out of the Nemo speech team, which NVIDIA has had for a while and has really been just pretty relentless in shipping new versions. So I talked about Parakeet on the channel before. That was one of their models. And this has sort of benefited from all those lessons of those models coming down to the 600 million parameter checkpoint. Now, I wouldn't say that it's perfect, but it is pretty amazing what you can actually do with this. And for me personally, just playing with it over this weekend, I'm already starting to use it instead of other models that I basically had running locally. All right, so one of the key things about this model is that it's what's called cache-aware streaming. So what does that actually mean? So what's going on here is that this basically solves the problem around sort of buffered streaming. The old way to make a non-streaming encoder work on live audio is to feed it overlapping chunks. And each time you're feeding it these overlapping chunks, you're taking a window of audio, you transcribe it, then you slide the window forward, but you overlap it, then basically sort of end up transcribing these in-between chunks or these overlap parts multiple times. And that means you end up reprocessing that overlapping audio at every step, repeating this sort of same work, and this sort of just adds to your delay. You're literally paying for that compute to re-encode the audio that you've already had encoded. So cache-aware basically flips that. Instead of reprocessing the overlaps, the model caches the encoder's self-attention and activations, and then reuses those cache states as new audio arrives. You can kind of think of this as like a KV cache trick that you use in LLM decoding, but for a streaming audio encoder. The work that you've already computed on those earlier frames is stored, so when the next chunk comes in, the model attends to the cached representations rather than having to recompute them from the raw audio. And this basically just saves on compute and speeds up everything. Now, NVIDIA reports that this can make it up to 17 times better. They're measuring it on an H100. I've been running it on the DGX. I definitely noticed that this is faster than the standard models, but my guess is that your mileage may vary depending on what kind of GPU you're running this on. And I should point out that I've been running it at full resolution, but literally just as I started to record this and look at this, people are already running quantized versions of this, and I think they have MLX versions already out, which is kind of amazing how quickly the community is moving. So one of the big things that will determine the speed, especially if you're doing this for live streaming, is, setting the actual chunk size. So in the code, they basically have, you can set the attention context size in here. And this inference setting is kind of trading off latency for accuracy. You don't need to change anything about the training of the model. This is just an inference setting that you set at runtime. And you can basically set those chunk sizes to be 80 milliseconds, 160 milliseconds, 320, 560, or just over 1 second. And I'll show you in the demo where I'm doing this streaming. that you certainly can see the difference between, say, the 80 millisecond transcribed chunks versus the 1 second ones. Now, for me, I don't notice a huge difference in accuracy. I'm sure it's there, and I'm sure for special use cases, you're probably going to notice it a lot more. For me, though, with the streaming element, it's more down to, do you want every word transcribed sort of almost like word or two words at a time, or do you want phrases being transcribed? And that's what sort of the 1 second one does, as opposed to the shorter chunk size. All right, so you can see here in the model card the reasons why they're saying you should actually select this model. They do talk about punctuation and capitalization. To be honest, I haven't found that to be great for the streaming version of it, but I kind of feel like even the best streaming models in the world are not always great at punctuation when you're actually doing streaming. All right, so one of the big advantages of this model is the ability to have different languages. So there are 19 languages out of the box that just work perfectly. You can even set it to sort of auto-detect for those, although you will probably have some mixed results if it's streaming. But once you set them, they should work pretty well. On top of those 19, they've got 13 ones which they say are production level for this. And then finally, they've got adaption ones. So this is 8 languages that the model can adapt to. So for example, Thai, I tried this one out, and with their base model, it really doesn't work properly at all. You need to fine tune it for this. So my guess is what they're saying is that they've had pre-training on these other 8 languages. But if you wanted to actually use them for anything serious, you'd want to go and fine tune them yourself. Now, I think they either have or they're in the process of releasing some of the fine-tuning code and some examples to do that. And I am sort of curious to see myself, like how much data would it actually take to fine-tune this model to be really good at Thai? And it's something that I may look at in the future. But generally, the way this works is you can pass this in as a code, and it's then doing conditional generation. So it's generating based on the input plus the code for the actual language to generate the output. So another feature that you can get working with this, which for me is really cool, is the whole idea of word boosting. So I think on some of the inference providers, they're providing this already. I was able to get it working with my own scripts in here. So if you don't know what word boosting is that you can think of all these kind of models as being biased towards what they heard most in training, right? That means like if there are certain words that are very common in English, it will default to that. And that's great for your average kind of vocabulary. The problem is, what if you've got things like product names or drug names or code names or, people's surnames or even things like model names that are much rarer and probably were never in the actual training data? Then the model does really badly at that. So a classic example of this would be my surname. The models are not going to basically get that right. And so in the past, what people would do is that they would fine tune for this kind of thing. That's not a great solution. It often tends to be sort of expensive, slow, and it can be really sort of overkill if you just want it to know 20 different product names. And then in 3 months from now, those products are going to change or something. Really, what you want to be able to do is pass those in at decode time. And that's exactly what word boosting actually is. It's a decode time technique. There are no weight changes, no retraining, no fine tuning. You're basically just handing the model a list of words plus some kind of strength, and then it becomes more likely to reproduce those words as opposed to other words that sound like those words. So this can be huge if you're trying to transcribe things with product names, with people's names and stuff like that. And people get really annoyed, and probably rightly so, if your system is constantly getting their name wrong or constantly getting something specific that they want wrong. So the model is actually using what's called a boosting tree to basically generate candidates and score them. And you can think of the word boosting is basically adding in your phrase. It doesn't have to be a single word. It can be a phrase in there into this tree. And as the decoder basically generates the tokens out, it sort of walks along these. And if it sees that, oh, your one is possibly relevant to this and it scores highly, it's then getting a positive bias added to the score. So it basically becomes more likely to get the highest score and then be what the model actually predicts out. Now, that's only going to happen when somebody says something that's close to that particular word or phrase. Obviously, if they're saying something totally different, the model's not going to be able to work out that, okay, these are the same things. Now, you have to play around a little bit with how strong do you want the boosting. If it's too high, you get false positives and stuff like that. If it's too low, it's not going to work. But generally, if we've got a list of words or phrases that they themselves are quite different, you can actually pass them in and get a strong result back. As I'll try to show you when we do this in the demo, you can do this both for the streaming predictions and the non-streaming predictions. All right, let's jump into the demo and have a look at how this model actually works. Okay, so this is actually testing the model running locally. So what I've got is I've got the model running on an NVIDIA machine. I'm streaming that through the local network to my Mac where I'm actually recording this. So let's see how it goes. So you'll see that I've got a few different things in here. You can select out the language that is going to be the right language for this. It could also be set to auto detect, although I find that auto detect is a bit hit and miss in here. You can then set out the latency. So we'll do some experiments with latency, and I'm just using the normal microphone that I would use. All right, so as you can see, the audio is starting to show up here. This is kind of the median latency that I've got set up, but it's able to stream it pretty good, and the accuracy of this is going to work out pretty well as well. And I actually find for sort of general use cases so far, the accuracy on the fastest one versus the slowest one isn't that much different. Okay, so I've just stopped it there. We will reset this. Let's go to the fastest one. So the fastest one, obviously, we're just taking smaller chunks of audio. So we're now down to 80 millisecond chunks of audio or 80 millisecond chunks of audio here. You should see that it's basically responding quicker because it's got more times that it's actually being able to process each of those 80-second milliseconds. It's still working out some sort of overlap and stuff like that. It's still going to be able to do this. And as you can see, the accuracy hasn't really gone down a lot, but we've got pretty good quality now streaming transcription of pretty much anything I say. And I can sort of stop, I can, start. Now, the other thing is we don't have perhaps great punctuation here. If I pause and say, okay, I wonder what's going to actually happen next if I keep talking here, you can see that we're not really getting anything great in the way of punctuation with this model. If I go all the way up to the highest accuracy, we're now over a second, and you're going to see that definitely it's going to be doing it in chunks. Now, but because those chunks are bigger, we're still going to have a pretty nice sort of transcription going on here. It's just that we're getting multiple words at the same time rather than sort of chunk by chunk where each chunk is almost one word here. This is still very good for running through the model. It's meant to be higher at the highest level of accuracy. I would say, though, I don't see a huge difference in the accuracy as we go through this. But the great thing is you've got the option to do this. Now, I was testing this originally using a Gradio interface that went through the web. And definitely there, I saw that, okay, things would actually slow down, especially with this one. But you can see in this case that really that's not a problem. It's able to keep going quite a long way. I've never actually gotten to the end, so I'm curious to see, like, okay, it looks like we've filled out the box there. Oh no, okay, so it was basically just catching up, and it's still going here. What are we going to see? It is very cool, I got to say, that NVIDIA is actually making these things available. And you will see that certain words, things like NVIDIA, it does really well at being able to transcribe that at words like Google, at Microsoft, all the common sort of nouns and pronouns, it will actually know them and be able to transcribe them pretty well. Where this doesn't do well is with words that it doesn't know very well. So, for example, if I talk about Nemotron, it seems to know what the Nemotron models are, but then sometimes it will say transcribe them correctly. And you can see sometimes it's transcribed it with an M as opposed to with an N there. Uh, the models from Quen are going to be spelt wrong. So really, Quen should be Qwen if we're spelling it in English. But you can see that when I just say Quen, it doesn't get that right. So this is where word boosting comes in. And I'll just point out that even if we do this with a faster, lower latency transcription in here. If I say the word NVIDIA, it can probably pick that up pretty well. If I say the word Quen, it's not going to be able to get that. So if I say Google, Microsoft, Apple, all those big companies, it kind of knows what they are, but it doesn't know Quen, doesn't know Minimax. Maybe that's probably something that it can get, yes. But you can see that if I say my name, for example, Sam Witterveen, it's going to get the Sam right, but it's totally gotten the wrong. It's totally got the wrong spelling there for the surname. So this is what we want to fix, and the way we're going to fix this is we're going to use word boosting. So this is a technique which I'll explain in a second, but you'll see that what I'll be able to do then is inject certain spellings for words that are how I want them to be spelled. And it's not a swap. It's not like I'm working out how it's saying it. I'm basically just increasing the probability of how it would actually come out. So let's look at that. Okay, so what I've done now is I've run a version of the script where we're actually boosting certain phrases or certain words, certain phrases. So it doesn't have to just be a word. This could be one phrase. We're basically just boosting the probability of those tokens in that order appearing. So you'll see that I just showed you before that things like Quen it was getting wrong, my name it was getting wrong, etc. If I put it on and I start talking now, we should see that it's starting to transcribe. And I say, hello, everyone. My name is Sam Witterveen, and I'm going to be talking to you today about the Quen models, about the Nemotron models, and about how they all work together. And you can see now it's got my name right, it's got Quen right, it's got the Nemotron models right. So this is something that I see a lot of times people don't realize, that you want to be able to do this with an ASR system. You want to be able to boost certain words and phrases so that they will appear more. And that will happen not just for that version. If I come in here with the quick version and say, right, my name is Sam Witterveen, and I'm going to talk to you about the Quen models, whether we're talking about Quen 36B, where we're talking about Quen. And you see, even if I come in with the lowest latency one, and I talk about, hello, everyone, my name is Sam Witterveen, and I'm going to be talking to you about the Quen models versus the Nemotron models. And we're going to start off talking about Quen 27 billion parameter model. Now, it seems to have missed the word model there, but the rest of it is done pretty good, okay, with this. And you'll see this is true even for the highest level accuracy as well. It's just that the chunks that we're going to get there are going to be longer. So if I'm talking here and I say, hello, everyone, my name is Sam Witterveen, and I'm going to be talking to you about the Quen 27 billion parameter model versus the Nemotron model. You can see here it basically got it right. If you just like all these things, they're not perfect, but that is basically word boosting. It's something that you can do with the Nemotron 3.5 ASR model. It's something that you probably want to do if you're going to put something into production. Okay, so the other thing that I haven't shown in here is speaker diarization. And there are a number of different ways that you can do this. You can either use an external model to do this, or you can actually do it with the Nemo framework. They've got a whole section for doing it in here. For me, I couldn't get this working well on the live transcripts, but certainly for doing things like podcasts and stuff like that, it works really well. And while it'll basically just section off and return back the different speakers, You can then pretty easily just substitute out speaker one for the name of that person, etc. The other thing that you can do is you can capture the embeddings of the speakers. So if you've got a little bit of the recording where you know this person, if, for example, at the start of recording, I say, "Hi, my name is Sam," and then you captured that and you took the embedding from that, you can then assign that to the different speakers and have it be able to actually return back the speakers and possibly be able to get that going with the live transcription version as well. So in general, I got to say, this is pretty awesome how useful this model is. And it's basically quite easy for you to run it locally to be able to do different kinds of ASR tasks like I've shown in here. So anyway, let me know in the comments what you think of this, if you've actually had a chance to try this out yet. Certainly for myself, this has been a productive use of just testing this model out and then incorporating it into some of the workflows that I've got that run on my local machines here. Anyway, as always, if you found the video useful and you're interested in videos like this, click like and let me know. If you've listened right through to the end, thank you very much for that. One of the things that I am thinking of doing is starting up a second channel to do much more sort of in-depth, long, perhaps not as polished and edited content, going through basically the code for this kind of stuff. I realize now when I end up showing too much code on this channel, the videos tend to go too long, they don't do as well, etc. But I do think there's perhaps an audience that is interested in just a little bit more visually boring, in-depth sort of code examples of some of these things. So if that resonates with you, please comment below and let me know what your thoughts are around what I should do and how I should do it and stuff like that. Anyway, I will talk to you in the next video. Bye for now.